Mic is working. Bouncing? All right. I will I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to bless our work today. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I have, I guess, an example for you guys. So I'll start with this one here. Suppose f of x comma y is equal to the exponential of x squared minus y squared. Find equation of tangent plane to z equals f of x comma y at 1 comma minus 1 comma what would z be if we're looking at the point 1 minus 1? What would the z be here? If what's the exponential of what? 1 squared minus a minus 1 squared, which is 1 minus 1. Exponential of 0 is 1. So the z coordinate would be 1 here. All right. Okay, so let's do it. Pretty basic problem here. If we calculate the gradient of f, well, I don't need to calculate gradient of f here. My bad. I mean, we could, but let's get to the point here. So z is equal to f of 1 minus 1 plus f sub x of 1 minus 1 times x minus 1 plus f sub y of 1 minus 1 times y minus a minus 1, which is y plus 1. That right there is the equation of the tangent plane. Now, I kind of like the gradient notation just as a means of, well, my bad. I'll make up my mind here eventually here. So f sub x is like 2x exponential of x squared minus y squared, right? And f sub y is what? Minus 2y exponential of x squared minus y squared. Why is there a 2x and why is there a minus 2y in front of the exponential there? These are the what? These are the chain rules, right? Respectively with respect to x and y here. And so using those formulas, but evaluating, you know, at the point 1 minus 1, what do I have? I've got, you know, z is equal to 1 plus what? F sub x of, what is this? We have 2 times x minus 1. And f sub y is what? Minus 2 times minus 1 times y plus 1. All right? So therefore, my tangent plane has equation z equals to 1 plus 2 times x minus 1 plus 2 times y plus 1. Right? And if you wanted, you could simplify that to, what is it? What I got? I got 1 minus 2 plus 2. So I think you could simplify that to simply 1 plus 2x, you know, plus 2y if you wanted. But, you know, I like this answer perfectly fine. This is a perfectly fine answer for this question. I'll box it there. All right? Does that make sense? So any questions about this? This is pretty plain Jane. Here's a function of 2 variables. Find the equation of the tangent plane to the graph. Like, this is pretty cut and dried. There's another way we could do this question, right? And let's look at it. Let's look at this problem from a different perspective. And so this is like, you know, alternate approach. And I wouldn't recommend this approach. It's like not as good an approach, really. But if we wanted to look at it parametrically, we could parameterize using x and y in this case. So like if I use x as a parameter, y as a parameter, then what's my formula for z? Well, e to the x squared minus y squared, right? So if you did that, that would be, this is a parameterization of the graph. Of the graph z equals f of x, y, right? And then if we take the parametric approach, then we'd calculate, partial r, partial x, which would give us what? 1, 0, 2x times e to the minus x squared minus y squared, right? And partial r, partial y, which would give us 0, 1, minus 2y, e to the minus, did I say minus x squared minus y squared? What's wrong with me? It's x squared minus y squared, right? E to the x squared minus y squared. And then to find the normal vector, we do what with these partial velocities? Well, the normal vector, using x and y as parameters, would be partial r, partial x, cross partial r, partial y, which if you tilt your head and squint, you can see how that works out. So like the x component, it's coming from this minus that. So I get a minus 2x e to the x squared minus y squared for my x component of the cross product. I look at the y component, that's coming from like z cross y, so it's actually plus 2y e to the x squared minus y squared. All right, and then the z component is just from these two. I just get a 1.
Why is the x component negative?
Cross product. So, when you take the cross product, it's this one. So this would be plus, but this is minus. But this is yeah.
Actually, I'll wait for my question. Sorry.
Oh, okay, that's fine. And so then the normal vector at the point we're interested, which was 1 minus 1, would be what, like minus 2, 1. So therefore, your equation is like minus 2 times x minus 1, minus 2 times y plus 1, plus 1 times z minus 1 equals to 0. And there you go. That's the equation of the tangent plane. And you can work that out. It's the same equation. Yes, sir?
So in the first question, I'm following through a lot of it. I just don't understand why I see why in the parameter, when you get the parameterization, you have after the x, y is the first one. When you add like f of x times x minus 1 and plus f of y.
Uh-huh.
Why does that happen? Because aren't you taking the dot product of the gradient with
Well, I'm not sure what you're after here. Like what are you talking about in the red or the black or the blue? Which?
The first one.
The first part?
Yeah.
Oh, this is just a standard result. We derived this the other day, that the equation for the tangent plane to a graph is given by z equals to f of ab plus fx of ab times x minus a plus f sub y of ab times y minus b. Like this is a known formula for us. So I'm just using it.
Yep. Got it.
This second approach here, I'm creating a parameterization using x and y as parameters. It's a very silly thing to do because of course what's above here is easier, right? Like we didn't have to take the cross product because if we know the formula we can just use it. But I want to point out to you that we can adopt this other viewpoint that we're thinking of it of x and y as parameters, and if we do that, we calculate the normal vector field. It will give us this right here. And what is this, by the way, guys? That is exactly minus fx minus fy 1, which is what we derived for the normal vector field of the level surface, which corresponds to the graph the other day. All right? It's not an accident that we got that there. So anyway, so which if I don't constrain you to use one approach or the other, which should you use for a graph? Like obviously up here. This is what you do if you have a graph, right? You just use the formula. But it would be good, healthy, if you understood how that formula knits together with the other two perspectives, right? One other example here, and then we'll move on. Example 2. Suppose we have f of x comma y equal to 4x squared minus y squared plus 2y. All right, and I want to find equation of tangent plane at x equals to minus 1 and y equals to 2, right? For graph z equals to f of x comma y, right? So here I want to do something like totally different. All right, this is completely off the rails what I'm about to do. I'm going to share with you one of my favorite algebra tricks. So we're looking at, here's the formula for the graph, right? Z is equal to, I'll put the 2y first. Oh, I'm fine, I'll keep it like this. 4x squared minus y squared plus 2y, right? So far nothing happened. I'm trying to find the tangent plane at minus 1 and like this and this, right? So this suggests to me I want to have an x plus 1 in my answer, and this suggests to me I want a y minus 2 in my answer, right? So here's a trick. I can trade x for what? I can trade x for x plus 1 minus 1. And I can trade y for what? For y minus 2 plus 2. Right? And again, y minus 2 plus 2. So all I've done is add 0. Right? And then I just do algebra. So I've got 4 times x plus 1 squared, I'll put some big parentheses in here, minus twice x plus 1, plus 1, close big parentheses, minus, start another big parenthesis here, y minus 2 quantity squared, plus 4 times y minus 2, plus 4, close big parentheses, plus 2 times y minus 2, plus 4. All right, so now I have everything expanded about the point I'm interested in. And let me just put the constant terms first. So there's 2 constant terms in all this, right? There's a very noisy snack in here somewhere. I had a class once in organizational industrial psychology, which met once a week. And like, if not for a meeting, a break in the middle where I could go get a very large cup of coffee, I would never have made it through that class because it was like incredibly boring. But interestingly enough, the lecturer for this class was one of like the top 10 most gifted lecturers in all the courses I ever took. So like, his lecture skill was nearly unparalleled, yet what he was talking about was so insanely boring that you could hardly make it through the class. But he had one rule, which is you could bring a snack, but it had to be quiet. So I also have this rule. But anyway, so this is for, I mean, what am I talking about? There's no snacks allowed in the classrooms, of course. And no shorts either. Well, that rule is obviously incorrect because I see shorts. But it's like the speed limit signs. They're all wrong, you know? Okay, and I know my audience. All right, very good. So anyway, so these 2 of these 4s, they'd be canceling it. It just leaves you a 4 out front, right? Am I right? There's just a 4? Okay. And then I have what? How many x minus 1s? I've got minus 8 times x plus 1, right? How many y minus 2s do I got? I got minus 4 of them here, but I got 2 over there, right? See this? Here and here? These 2 guys, they combine. What do we got? 2 times y minus 2, right? And then what? Well, then I've got higher order stuff, right? So plus 4 times x plus 1 squared. That was a minus 2? Oh, yeah, the minus wins, doesn't it? Thank you. Plus 4 times x minus 1 squared, and then, of course, minus y minus 2 squared. And I think that's actually just true. All right? Here's the thing. If you can write a formula like this for your function, you can just straight up read off the equation for the tangent plane. Because what the tangent plane is the best linear approximation to the function at the point of tangency. What's the best linear approximation to this apparently like some sort of like hyperboloid? Well, you just, right here, these guys. The equation for the tangent plane is straight up z is equal to 4 minus 8 times x plus 1 minus 2 times y minus 2. There you go. We just found the equation for the tangent plane using algebra. No calculus in sight.
What happens to the dropped off portion of that?
Well, those are not part of the linear approximation at the point. If we think about being very close to the point, minus 1, 2, what happens? This and that are super tiny comparative to this. Like this is much, much bigger than these close to the point of tangency. And for that reason, this is the best linear approximation. Now, of course, you could derive this with calculus much easier, right? So like, well, this is dumb. Why are you doing this? You could just as well have said f sub x is what? F sub y is what? The x derivative here is what? It's 8x. The y derivative, negative 2y plus 2. Indeed, this is the smarter way to do this. But I wanted to show you that you can think a different way. You don't have to be hostage to my calculus if you're willing to think. So, you know, that's minus 8. And this is what? Minus 4 plus 2, which is minus 2. That's not an accident. Right? See that? And actually, this is the start of a story that I'm not going to complete today, but it's actually an interesting story, which is how. Okay, great. So the tangent plane is the first approximation to a function of several variables. Like it's the best linear approximation to a function of several variables, right? So what's past that? How about like the best quadratic approximation, right? Or the best cubic approximation if we allow ourselves, you know, higher powers in the expansion point, right? Can we do that? Is there such a concept in Calc 3 as well? In fact, there is. There is something called the multivariate power series, which we'll talk about in a future lecture. This is just a foreshadowing example. All right. With that, now that we're all here, I've gotten in the habit of trying not to start new material at the start of class because there's like inevitably some amount of people trickling in after the start of class because stuff happens. So let us start the genuinely new topic, which is partial differentiation with side conditions. Partial differentiation with side conditions. And so this is really the last, I guess, thing I have to really teach you about just basic theory of differentiation of functions of several variables in here. And this is a little subtle. It's a little subtle. So let me begin with just a reminder about the total differential. So we did introduce the total differential the other day, right? So I guess I'll skip straight to my example. All right, so my example 3 here. We can think about W equals to xyz. All right? And if we think about this, we could take the total differential of this, right? And what would that be? dw would be what? It would be, we got yz dx, right? Plus what? Plus xz dy plus what? Xy dz, right? So what are these coefficients here? This is what? This is partial w, partial x, right? This is what? Partial w, partial y, right? And this guy here is partial w, partial z, right? Great. So we have that. On the other hand, I could solve this for z, right? Z is equal to what? W over xy, right? And I could take the total differential of that, couldn't I? And what would that tell me? See, now I have to do the partial derivative of the reciprocal of x, which gives me a what? Minus w over x squared y, right? Dx plus what? Now the y derivative, right? So minus w over xy squared dy, right? And then what? Yeah, plus 1 over xy dw, right? And so the meaning of the coefficients now are what? This is what? This is partial z, partial x, right? This right here was partial z, partial y. And this right here is partial z, partial w. There's something kind of neat here to notice, which is that if we call this equation here star, right? Solve star for dz. What does it give us? dz is what? We get ourselves like a dw minus yz dx minus xz dy, all divided by what? Divided by xy, right? And so what we're looking at here is like minus yz over xy dx minus xz over xy dy plus 1 over xy dw. But supposedly, right, these should also be what? Like this should be that, right? This should be that, and this should be that as well, right? In fact, it's pretty obvious that the dw coefficient's the same. I mean, they're manifestly the same. But how about the dx and the dy coefficients? Are these simpatico? At first glance, it looks like maybe not, right? But what happens if we, well, let's see here. I want to put the denominator, listen to me, the numerator is w, right? So if I add an x to the top, right, if I multiply this by like x over x, then I get minus w over x squared y dx. And again, multiply this one by y over y, this one, right? And what do we got? We got minus w over xy squared dy plus 1 over xy dw. Look at that. the same. What does this show you? So I told you guys when I talked about the differential the other day that we can think of the differential as a means of formally remembering a whole bunch of partial derivatives all at once. And it turns out that the calculus is so kind that we can actually do algebra on the differentials, and it will cohere with this notion of the total differential, like recording partial derivatives. So in this context, like if I write dz is equal to, a dx plus b dy plus c dw, that tells me that whatever goes here is my, partial z, partial x. And whatever goes here is my partial, partial z, partial y. And whatever goes here is my partial z, partial w. On the flip side, if I have, like up here, dw equal to stuff with dx, dy, dz, then the meaning of the coefficients are partial derivatives with respect to w, of w with respect to x, y, and z respective. All right? But there's a deeper thing that's maybe not apparent. It's like a little bit below the surface here, but there's a way you can get confused, and let me try to confuse you. So here's a definition. If u and v are independent variables, that was supposed to be independent, use your imagination, then partial u, partial v is equal to 0, and partial v, partial u is equal to 0. This is a way we can characterize independence of variables with respect to partial differentiation, is that the partial derivatives of the variables with respect to each other are 0. We've already seen this with x and y, right? So with x and y, goodness. Remember, we proved that partial x, partial y, and partial y, partial x were 0. That is showing you, in particular, that x and y are independent variables, right? In our context, for functions of two variables, right? Unless we say otherwise, x and y are not intertwined, right? They're taken to be independent variables. Okay? So here, on the one hand, look at this. I have, in this calculation, right here, I have that partial z, partial x is equal to minus w over x squared y, right? But if I think about it up in here, up in this universe of discourse, I would say that partial z, partial x is equal to 0. In fact, I need to assume that partial z, partial x is 0 in order to derive, like, these formulas. How can I have partial z, partial x being 0? How can I have that partial z, partial x is 0? But I also have that partial z, partial x down here apparently is minus w over x squared y. How can I have both of these? What gives? Context is what gives. These are different contexts. You see, the full notation here is that this is partial z, partial x, right? It's part of this story down here. We're using the variables, independent variables, x, y, and w. So notation for that, I put a y and a w here. That tells me I'm partial differentiating z with respect to x, holding y and w fixed. If I do that, that's what happens. On the other hand, partial z, partial x, holding up here, y and z fixed, well, that's just 0. Because if you hold z fixed, the derivative of z with respect to x is automatically 0. So this is the notation we need. We need notation which tells the reader what is your set of independent variables. What is your set of dependent variables? Because your choice of dependent or independent variables will change what the partial derivatives are, even with respect to the same variable, in this case x. Let me show you, like, it's kind of, I still feel like this example is slightly forced. Like, the larger point in this example is, like, it's very, to me, I was very excited, personally, when I found out that I didn't have to do this differentiation. You see that? I don't have to do this differentiation because it's much easier to simply take star and solve for dz. Solving for dz doesn't require reciprocal, like, you don't have to differentiate 1 over something. You just solve for dz. Immediately you have all the partial derivatives. You get 3 partial derivatives simply from algebra here. That's really more the point of that example. Let us look at another example. All right. So the solution to the ambiguity is simply to write more. All right. That's oftentimes the case. This is one of the weaknesses of Stewart's calculus. It doesn't appear in that book so much. So here's just some thoughts. If if w, x, y, and z are variables, then we have dw is equal to partial w, partial x, dx, plus partial w, partial y, dy, plus partial w, partial z, dz. Or, alternatively, we could write dx is partial x, partial w, dw, plus partial x, partial y, dy, plus partial x, partial z, dz. Now, at the moment, these are not yet unambiguous, all right? So to be clear, let me add some comments, right? So you guys tell me. So what do we mean by that? If we have dw is partial w, partial x, dx, which variables are we holding fixed in this differential expression? Like, how should we understand this? We want to think about that. Yes, y and z are my other variables here. This one, x and z, very good.
Oh wait, no, sorry. Yeah.
X and y, right? So always, basically the complete set of independent variables is listed in all of these properly understood. All right? And down here, my set of independent variables, see, I'm thinking of dx, let me write a little bit more here. So I put a y and a z here. I put a w and a z here. I put a w and a y here. Let me give you a little bit more language. So this, we have w is equal to w of x, y, z. So these are independent, and the w is the dependent variable. That's the story for this one. The story for the second equation, right, is what? So you guys tell me, what's this one? What's the story here? X is what? The dependent variable. And here we're using w, y, and z as the independent variables. All right. So let me show you. So all right. So here, the context here is pretty much I've got like 4 variables, and I'm just writing 1 in terms of the remaining 3, right? Sometimes our context might be 4 variables, but we have 2 equations. All right. So let's think about that for a second. What happens if we have like our universe is 4 variables, but we're dealing with 2 equations that bind those 4 variables? Well, my next example is that kind. And I think this example is kind of a little bit more interesting in terms of how this math works out. So, example. 4, I guess. Yeah. No, it's not just that. It's something else. I mean, there are ways of understanding what we're doing in terms of thinking about we're partial differentiating variables that are stuck on some surface, but me blathering on about that won't give you any kind of additional insight into the calculation, so I'm going to resist the temptation to try to give geometric insight here. So here's another problem. We have W equals to, but now you've tempted me to talk about geometry, so I probably will. W equals to x plus y plus z, and x plus y is equal to wz, right? And our question is to calculate partial w, partial x, holding y fixed, and we want to calculate partial w, partial x, holding z fixed. And I want to show you that those are different. So if I just asked you to calculate partial w, partial x here, in this context, it would be an ambiguous question, is really my point. All right? So there's different ways to go about this. All right, so let me show you just sort of direct ad hoc approach. We're trying to calculate partial w, partial x. I've got 2 choices. I can either use this or that.
This.
Use the this? All right. So partial w, partial x, and we're doing what? We're holding y fixed. So I'm going to do partial x holding y fixed of x plus y plus z. How does that work? How does this calculus work? What's partial x, partial x? Well, guess what? Still 1, right? Now we're doing partial y, partial x, holding y fixed. Well, if you hold y fixed, what happens? That's just 0, right? That's just 0. However, partial z, partial x, holding y fixed, well, that's not necessarily 0 because we're not fixing z. It is what it is, right? So what we have here is 1 plus partial z, partial x holding y fixed. Now, if I didn't have the second condition, that would be it. It would just be partial z, partial x holding x, y, and z fixed. Well, that would just be 1. But that's not the question. We have another condition. See, we have x plus y equal to wz. What can we do with that? This here tells me that I can differentiate that equation, holding y fixed both sides. Right? So what does that give me? It gives me 1 is equal to, well, partial w, partial x holding y fixed times z, plus w times partial z, partial x holding y fixed by the product rule. So in this problem, you guys tell me, well, we're not done yet, but what are the dependent variables and what are the independent variables in the calculation I'm currently doing? Think about it. I'm using x and y as independent variables here, right? So z and w are the dependent variables. So I'm trying to calculate right now partial w, partial x holding y fixed, right? It's kind of annoying because at this point I've got what? Look at what we got. I've got this equation number 1, right? And I've got this equation number 2. What is this? This is 2 equations and 2 unknowns, right? I just want one of them. At the moment, I don't really care what, partial z partial x holding y fixed is. Like, I want to get rid of that, right? So what should I do? I think this number 1 is easier to solve for, right? Take number 1, and from this we get that partial z partial x holding y fixed is equal to what? It's partial w partial x holding y fixed minus 1, right? So take that. Take this gadget right here and substitute that bad boy right up in here. And that should give us one equation in the one unknown that we're looking for. So we get 1 is equal to partial w partial x holding y fixed times z plus w, big parentheses, partial w partial x holding y fixed minus 1, close parenthesis. Now we can solve for partial w partial x holding y fixed, right? Which gives us what? One plus w divided by z plus w. All right, so like once you understand the rules of this game, it's relatively simple. It's just we just have to be methodical and not assume things aren't what they aren't, right? Like I can't assume that partial z partial x is 0 here because it's not. It's bound by this equation up here, right? So how would the other calculation go? I want to find partial w partial x holding z fixed. How would that calculation go? So would you guys want to start with this or that? This? All right. So partial w partial x holding z fixed is partial x holding z fixed of x plus y plus z, right? Which now, I'll write it out, is partial x holding z fixed, right? It's still 1. Partial y partial x holding z fixed. Now this is not 0. But the partial z partial x holding z fixed, well that is 0. So we've got 1 plus partial y partial x holding z fixed. That's my partial w partial x holding z fixed. Let me call that equation 1, because I think you can probably see where this is going to go. Maybe I should call it equation 3 since we already had 1 and 2, right? So now I differentiate the other equation, right? So I also have partial x holding z fixed of x plus y is equal to partial x holding z fixed of wz. Now I think this one actually works out easier, doesn't it? Because how's that go? So we get 1 plus partial y partial x holding z fixed. Now if z is fixed, what can we do in the other derivative? It's okay, I'm going to kind of split the difference here. You're fine. So look, like z is a constant with respect to this differentiation, right? So essentially it just pulls out. And what you've got is just z times partial w partial x holding z fixed. Let's call that equation 4. Now we're trying to find this guy up here, right? So can you guys tell me what I should do? Whoa, dudes, look at that. This and that are the same. So I can just equate the equations and I straight up get equals what? Partial w partial x holding z fixed, yeah? Which, you said it means it's 0. I think you're right. That feels wrong. I have to check my notes here in a second. So, yeah, it looks like partial w partial x holding z fixed is 0. If I haven't messed up the algebra here somewhere. Let me check. Let me cheat. Oh man, I got a 2 here. Oh? Oh. Well. You know, the trouble is, it's hard to judge whether or not your answer is really wrong because these expressions have to be judged with respect to both of these equalities. So there's ways to make the answer look really different. So I'm not confident that I'm not sure about the notes being wrong. Or about the board work being wrong. But you guys see anything that, I mean, the rules I'm using are the rules, all right? Well, there's another way we can check our answer. So let me show it to you. So do you remember in my example over here, I just showed you, like, we could just solve for dz to find the z derivatives, right? We can do something similar here. So I'll show you guys the cheat code for these calculations. So what we do is take the defining equations and take the differential. So like, I've got dw is dx plus dy plus dz from my first equation, all right? And from the second equation, I get what? I get dx plus dy is equal to what? zdw, right? Or if you like, wdz plus zdw, whichever one you want to put first, right? So I just took the differential of the equations which govern our variables. All right? So we've got 2 equations in 4 unknowns, basically, right? So if we want to, all right, so like let me put some words here. So the second half of this calculation, we're using W and blank as dependent. W and what are dependent there? Y. The first half of this example, we're using what? I said it before, but I'll say it again. We were using Z and W as dependent. All right? So if I want to understand the derivatives with respect to the dependent variables y and w and y, I want to solve these for basically dy and dw. So I have let me just show you how that's done. So we have like dw, I'll do dw minus dy is equal to dx plus dz from the first equation, right? And this one here gives me what? Well, let's say minus z dw, all right, plus dy is equal to what? So I did nothing more than just solve this equation, rewrite it, okay? Right now I'm trying to solve this, I'm trying to rewrite that one with the w's and y's on one side and the x's and z's on the other. So what do I have here? Say again? Negative dx plus w dz. All right. How can I eliminate dy? Add the equations. Very good. Don't tell the other math professors I did this. So that's 1 minus z times dw is equal to 1 plus w dz. And from this, I see that dw is equal to 1 plus w over 1 minus z dz. And how many x's are there? Big fat 0, right? 0 dx. So therefore, partial w, partial x holding z fixed is equal to 0. And there is a mistake in my notes. Which I shall fix, along with the other many of them. Okay, so if you guys find a typo in the notes, you can email me about it. It is worth a bonus point. Okay, anyway. So that's that, right? But by the way, what else did this tell us? This told us more than just that, right? This also told us that partial w, partial z, holding x fixed is what? It's that. 1 plus w over 1 minus z. Actually, so what I'd like to sell you on is for these kind of problems, it's actually much smarter to just take the differential of the equations and to solve for the differentials that you're interested in the derivatives of. Right? So like, to rework the first problem to check my answer, what would we do if we use the method of differentials? Instead of solving, like it's the same starting point, right? Let me give this thing a name. Pac-Man, all right? To redo this business over here, I should solve Pac-Man for what? I'm using z and w as dependent, so I want to for dz and dw. I want to isolate dz and dw. So that's easy enough to do. I've got dw minus dz is dx plus dy from the first one. And the second one gives me, oh, it's already there. So z dw minus w dz is equal to dx plus dy. Whoa, dudes. Is that right? Positive what? Oh, it's a plus w? Okay. So how can I mean, the question is, how do you solve two equations and two unknowns? Do you guys know? I mean, there are various approaches. I personally like multiplication by a 2x2 matrix is like a really nice way, but I won't do that at the moment. If we want to make these equations match up, I'm trying to solve for what? I'm trying to solve for, I want to find the derivatives of w, right? So I'm trying to solve for dw right now. How do I solve for dw? I guess I could divide the second equation by z, right? And then I can, oh, that was the wrong thing. I'm trying to solve for dw, right? I want to get rid of the z's. So what should I have done? The exact opposite thing, right? I should have divided by w. Now I can add those equations and cancel out the z's. Right? Add these, and that gives me 1 plus z over w. dw is equal to, 1 plus 1 over w dx plus 1 plus 1 over w dy, which then tells me that dw is 1 plus 1 over w divided by 1 plus z over w dx plus 1 plus 1 over w divided by 1 plus z over w dy, which we could clean up a bit, right? What do you want to do here? Multiply by what to make that prettier? How about multiply by w, right? Over w, which gives us what? W plus 1 over w plus z, right? dx plus w plus 1 over w plus z dy. And what did we find? Oh, look at that. This right here, my friends, means that partial w, partial x holding y fixed is equal to, w plus 1 over w plus z. And that is exactly what we found by the other less clever method, right? By the straightforward, just use the independence of the variables and carve through it bit by bit, right? So I refer to the calculation method we were using to start with, I would call that the ad hoc method, whereas this is the method of differentials. Notice that with the method of differentials, we automatically also learn that the partial derivative of w with respect to y holding x fixed is w plus 1 over w plus c as well. So the method of differentials, it does a bunch of things at once. It gets you a whole bunch of partial derivatives all at once. It's really cool. All right, anyway. Now I have shown you my secrets. So this is the method of calculation. At this point, I will look at some simpler examples for you guys.